Right, a very good evening to all of you. Welcome to another revision session, and today we are going to discuss organic spectroscopy. Okay, so before I begin, I would like to clear this out that this particular session is not exhaustive. What I mean by that is not all topics are covered because spectroscopy is vast. Okay, so selective topics which are relevant to the examination that I have taken, and let's begin. Okay, so there are three topics that I've covered, that is IR, mass, and NMR spectroscopy. Okay, so first we will talk about IR spectroscopy. This is the general formula for calculating the frequency of the wave number for a IR for any molecule, that is 1 by 2 pi c under root k by mu, where k is the bond constant, that is basically denotes the strength of the bond, and mu over here is the reduced mass, okay, which is equal to m1 m2 upon m1 plus m2. This is the formula for reduced mass. Okay, so these are the two important aspects, that is a bond constant and the moment of inertia, on which your stretching frequency will depend upon. Okay, now these are some of the standard stretching frequencies that I've taken, and among them carbonyl stretching frequencies are the most important, so we are going to discuss that in detail. So we have OH bond. OH stretching frequency in free form is around 3600 centimeter inverse, and when it is hydrogen bonded, it basically comes down to 3200 to 3400 centimeter inverse. For nitrile it is around 20 to 60. For your mercaptans it is around 2550. For your NH it is from 3100 to 3500, and for the CH it is 2850 to 3000. So these are the general range for the IR stretching frequencies for the single bonds: OH stretching, nitrile, mercaptan, amine, and your CH bond. Okay, now how does the IR stretching frequency vary? Just a general trend I have shown over here, that as you go from, so this basically is depending upon the K value, because if you see over here, both are carbons, so the moment of inertia is the reduced mass is going to remain the constant over here. Okay, the reduced mass is going to remain constant. So what is going to change? The bond constant. Okay, so you can see over here that C triple bond C is a stronger bond. Okay, the bond strength of a C triple bond C is stronger, so the K value increases. If the K value increases, you can see the stretching frequency has increased, so it is 2150 when compared to the alkene, which is around 1650, when compared to the CC bond, which is around 1200 centimeter inverse. So you see that this is dependent upon the bond constant, because the reduced mass over here remains the same. But when we come on to the to these atoms over here, you can see that the moment not the moment of inertia, the reduced mass is constantly increasing. Okay, so over here you can see there's carbon and hydrogen, so it will have a less reduced mass. Over here we have carbon and chlorine, so the reduced mass is going to be more. So over here the reduced mass is dominating, and because the reduced mass is high for this, so you can see that the stretching frequency is around 1750 centimeter inverse, because reduced mass is high, and reduced mass is inversely proportional to moment of inertia. So in the examination, if some other examples also come up and they want you to arrange them according to the stretching frequencies, then keep in mind that these are the two factors on which it depends. And if the mass of the molecule is very high, or the atom for which you are trying to calculate the stretching frequency, then remember it will dominate. Okay, so if the reduced mass is very high, then that will dominate. Otherwise, if the reduced mass is almost similar, then the bond constant will dominate. So these are the two factors that you need to keep in mind. Now coming on to the hydrocarbons. So if you see this particular alkyne, now in the case of alkyne, you see there's a stretching frequency. The CH stretching frequency I told you was 2850 to 3000 centimeter inverse. That is the wave number for the stretching. But here I have shown you the stretching frequency of the CH bond as 3300. So you can see why is that? Because this carbon is now sp hybridized. So if this carbon is sp hybridized, it has more s character, it will hold on to the hydrogen more stronger. So this bond will the bond constant will increase over here. So everything you have to relate to the bond constant or the reduced mass. Okay, now coming on to the hydrocarbons. In hydrocarbons there are two exceptional there are two features. Okay, again over here, if you talk about the C double bond C stretching, so in this case we are talking about the C double bond C stretching. So this is your allenes. Okay, this system is your allene, and in the allene system you can see that this carbon over here is sp hybridized. Okay, this carbon is sp hybridized. So what happens due to this? The stretching frequency observed is around 1940 centimeter inverse, whereas for a normal C double bond C we observe around 1650. Okay, so you can see that there's a sharp increase in the stretching frequency, because again over here the carbon is having a sp character. Now when we go to cyclopropenes, in cyclopropenes also you'll see a very high stretching frequency, because this carbon, as you can see, is like the carbons in the cyclopropane are very you can see sterically strained, and because they are strained, they have a high S character, and again due to that reason over here you can see a high stretching frequency for cyclopropene. And as the strain reduces, that is from 3-membered ring you go to 5-membered ring, the strain has reduced, and that is why the stretching frequency is also reduced to 1657 centimeter inverse. But this is for a exocyclic double bond. You can see this double bond is on the outside. This is called the exocyclic double bond. It is outside the ring. Okay, but for the endocyclic double bond, you observe something very different. You observe that the stretching frequency decreases as you go from like from a 6-membered ring to a 4-membered ring. You can see constantly the stretching frequency is decreasing. Okay, why is that? Because over here a little complicated phenomena also comes into the picture, which is something to do with coupling. Okay, so since it's a very short revision video, I am not going to get into the detail of the mechanism or the reason behind that, but there is one exceptional case, and that is why I have taken over here, that for the endocyclic double bond you can see that it is continuously reducing the stretching frequency, but suddenly for the cyclopropene it again increases. Okay, for the cyclopropene it again increases, and the same factor that I told you about the coupling. Okay, so the coupling value over here, what in cyclopropene, what happens, the coupling value suddenly increases a lot, and because the coupling value suddenly increases a lot, you observe a high stretching frequency. That's why I've highlighted in orange also. So please remember this exception, that for endocyclic double bond the trend is that the stretching frequency decreases as we go to a smaller ring, but in this case of cyclopropene it actually increases due to basically coupling of C. So basically what happens, along with the C double bond C stretching, there's a coupling with a CC bond. Okay, so both of them couple, and because of that the stretching frequency increases. This is the only short explanation that I can give you. Okay, but remember, for the exocyclic double bond this is the case. For the endocyclic double bond this is the trend. Now coming on to hydrogen bonding. So sometimes what might happen is that they might not directly give you that hydrogen bonding is taking place. They might give you a molecule like this, which is methyl salicylate in this particular case, and they might ask you the carbonyl stretching frequency, or they might ask you the OH stretching frequency. So here you have to immediately comprehend that there's a possibility that the hydrogen bonding will take place, and once the hydrogen bonding takes place, you know that the OH stretching frequency will decrease from 3400 to from 3600 to some lower value, and similarly the carbonyl stretching frequency for the ester will also decrease. Okay, we'll talk about what are the carbonyl stretching frequencies for the different functional groups, but over here due to hydrogen bonding both will decrease. So the stretching frequency will be lower for the alcohol and also for the carbonyl group, whatever it might be. Okay, so let's come on to the very important topic, that is carbonyl stretching frequencies. Most of the questions that have been asked in CSIR have been asked on this topic. So this is something that you actually need to memorize or understand, whatever way works for you. Okay, it is better to understand because it goes in a logical fashion. So for amide, the stretching frequency, these are general values. The stretching frequency is around 1675. For a carboxylic acid it is 1710. For ketone it is 1715, for aldehyde 1725, for ester it is 1735, for an anhydride it is 1760, for acid chloride 1800, and there are two anhydrides. Okay, this is band 1, so there are two bands in an anhydride, and this is band 2. Okay, that's why you observe two stretching frequencies for anhydride. So this is the general trend which you need to remember. And one more thing is that if we have a conjugated acid, for example, let's say we have a double bond which is in conjugation with the ketone, or if it is in conjugation with the acid. So if there is a double bond which is in conjugation, or a aryl group also, for example, if we have a benzaldehyde, okay, a aryl group attached to a aldehyde. So in this case what happens, they are conjugated with, in this case the aldehyde is conjugated with the aryl group, in this case this ketone is conjugated with the double bond. So wherever there is a possibility of a conjugation, there is definitely a chance that their stretching frequency might also go below 1700 centimeter inverse. Okay, now this is one very good example that I found, and I thought I'll discuss it because again such exceptional questions can come in the examination. So over here if you see, the only difference between these two Decalene system is that in this case the chlorine is in the equatorial position. Over here it is in the axial position. So what you observe, that when the chlorine is in equatorial position, the stretching frequency for the carbonyl group is around 1750. Now what is the general value for ketone? It is around 1715, but over here you observe around 1750. So why is there a very large increase? Because in this case there are the lone pair of the chlorine and the lone pair of oxygen, they repel each other, because of which what happens, this bond becomes very rigid. Okay, because of this steric repulsions, this bond over here becomes very rigid. Okay, because of the strain. So this molecule is under strain, just like a cyclopropene molecule, like we discussed in the case of cyclopropene. Because of the strain, the stretching frequency is high. Over here also, this molecule gets strained. Whereas over here, there is no strain because the chlorine is now in the axial position. That is why you observe a stretching frequency at 1725. Okay. And similar to the conjugation concept that I was talking about, in ester also, it is very common to see the conjugation with the aryl group or with this alkene. So you can see over here we have the aryl group conjugated with the ester, and over here we have the alkene conjugated with the ester. Sorry, this is not ester, actually this should be OR. Now it is an ester. So the stretching frequency, you can see, goes down to 1715. So for ester it is generally around 1735 to 1740, but over here you see that due to the conjugation the value has decreased. But one particular mistake that a lot of students make is that sometimes the aryl group is given on the other side of the oxygen. Okay, so you see that now the aryl group is not in conjugation with the ketone. So in fact, now the opposite happens. The stretching frequency increases from 1735 to 1740 to 1765. Okay, so don't make this mistake. You have to see whether it is conjugated with the carbonyl group or not. Over here, it is attached to the oxygen. It is not in conjugation with the carbonyl. Okay, so please do not make that mistake. Now let's go to, okay, there's one more exceptional case, which is with amides. So in generally, when I said the conjugation happens, so due to the conjugation, the stretching frequency should actually decrease, like it happened for ester, for ketones, for aldehydes, and for carboxylic acids. But for amides, opposite happens. That means that if for amides we discussed the stretching frequency around 1675 to 1680. So this is a general stretching frequency. But when amides come in conjugation with the double bond, for example, over here with the alkene, the value increases up to 1700 also sometimes. So now why is this the trend with amides? The reason being, the stretching frequencies of amides is so low, 1680, because it is in conjugation with a lone pair of electrons. Now what happens, because it is already in conjugation, this particular carbonyl group is already basically in conjugation with this amine NH2. What happens is this double bond actually is not able to conjugate with this ketone, because now this particular carbonyl group is already sufficiently conjugated with the NH2. So now what happens is this carbon actually acts as an electron withdrawing group because it is sp2 hybridized. So instead of seeing a decrease in the stretching frequency, you see an increase in the stretching frequency, right? So this is the importance. Now coming to mass spectrometry, there are 2 or 3 important principles. For mass spectrometry, there has been one question on metastable peak. So what exactly is a metastable peak? Metastable peak is actually peak which is observed, which is a non-integral peak. So generally you observe integral peaks in the mass spectrometry, but sometimes what happens when a fragment is very short-lived, okay, then for those short-lived fragments, you obtain a metastable peak, okay. And for example, if there is a fragment M1 and that is fragmenting to M2, okay, then if we have to calculate that what will be the value of the metastable peak, then the formula is directly m2 square upon m1 square. That means mass of the second fragment squared upon the mass of the first fragment. Okay, so if you want to practice one question, it has been only asked once in December 2014 examination for 2 marks, so you can go ahead and solve that question. Now coming on to the 2 important terms. So there are 2 important terms, which is one is the molecular ion peak and one is the base peak. So molecular ion peak basically tells us about the mass of the particular compound, that what exactly is the molecular weight of the compound under study. And the base peak is the most stable fragmented peak. Okay, so sometimes the molecular ion peak can also be the base peak, but base peak is actually the most stable fragment. It could also be the molecular ion peak. Okay, so molecular ion peak is basically, if this is the mass spectra, the molecular ion peak will be the last peak that you'll observe. So like for example, these are the molecular weights 100, 200, 300 like this. So this will be the molecular ion peak, and the base peak is the most intense peak in the spectra. That is called the base peak. So sometimes it might also be the molecular ion peak depending upon the molecule. Okay, now these are the most important questions based on isotopic substitution. So for that you need to know the percentage of isotopes of various compounds. Okay, now how they will ask the question is that they might ask you the ratio of m:2 m+2 peaks. Okay, they might ask you the ratio of m:2 m+2 peak. So for that, for example, if the compound has chlorine, then you should know the isotopic abundance of 35 chlorine and 37 chlorine. That means both the isotopes. So they are basically in the ratio 3:1. So the m:2 peak will also be in the ratio 3:1. Okay. Similarly, if you talk about bromine, in bromine they are in 1:1 ratio. That means 50% both the isotopes are present in 50% abundance. Okay, if you talk about sulfur, the 32 isotope of sulfur is, let's say, in 100%, then 34 sulfur isotope is 4.4%, and 33 sulfur is 0.78%. So these are the relative natural abundance of the sulfur isotopes. Similarly, if you talk about carbon, it is for 12C, it is, let's say, 100, then for 13C it is 1.08. So the isotopic abundance is roughly taken to be 1.1%. Fluorine is absolutely pure. For hydrogen also, we have certain isotope of deuterium in the natural abundance, but that value is very, very low. So we generally take it to be 0 only. But there is some, you can say, isotope of the deuterium atom also along with the hydrogen, but that is very, very negligible. Similarly, for nitrogen also, 14 nitrogen if it is 100, then 15 nitrogen is around 0.38. So again, you can see the value is very, very low. Only for carbon you see around 1.1%, and for sulfur it is 4.4. Okay. Now let's move forward. Okay, so yes, so in case I feel that there could be one important question that comes from the for a hydrocarbon. So for example, a hydrocarbon is given, and I told you that for hydrogen the isotopic abundance can be taken to be 0, even though it is not 0, it is some value, I think 0.0016 or 0.016. There is some value. If you want, you can go ahead and check it out on internet. So if for example there's a hydrocarbon given to us, let's say they give the question that there's a molecule called 18 aniline. So calculate the ratio of m is to m plus 1 peak. Okay, so in 18 aniline molecule, you know, there are 18 carbons. Okay, provided you are taking the hydrogen has 100% isotopic abundance, or you are ignoring the hydrogen, and they ask you the ratio of m is to m plus 1 peak. So you know that 13 carbon is 1.1%, and they are asking you m plus 1 peak. So all you need to do is take the number of carbons. So if, for example, if the molecule is 18 aniline, you take 18 carbons and multiply it by 1.1. So you will get a rough value of around 19.8. So what will be the ratio? Ratio will be 100 is to 19.8, which you can take it to be 20. Okay, so the ratio will come out to be basically, let's say, it will come out to be 5 is to 1. Okay, so this will be the ratio of the m is to m plus 1 peak. So basically what you need to do is take the number of carbons and multiply it by 1.1. Similarly, if they give you the isotopic abundance of hydrogen, let's say it is 0.016, and in a molecule there are 20 hydrogens, then you need to do the same. Number of carbons into 1.1 plus number of hydrogens into whatever is the isotopic abundance of that particular molecule. Let's say there are 2 nitrogens. So m is to m plus 1 peak will be, I'll write down over here. So let's say we have carbon. For carbon it is, number of carbons are, let's say, 18. So 18 into 1.1 plus, let's say there are 2 nitrogens. So 2 nitrogens have a isotopic abundance of like 15 nitrogen has the isotopic abundance of 0.38. So that will also be counted as m plus 1 only, right? Because we have normally we have 14 nitrogen, and now we have 15 nitrogen. So let's say if the nitrogen is also there, then we consider 2 into, like there are 2 nitrogen atoms, so 2 into 0.38. So this is how you have to do the calculation. Okay, now and if they ask you m plus 2 value, then for carbon this is the formula. Generally, I've seen that questions have not come in CSIR, but in other examinations, questions have come on m is to m plus 2 peak for carbons. Okay, generally they only consider carbons. So again, the formula is number of carbon atoms into 1.1 upon whole square. First of all, number of carbons into 1.1 whole square upon 200. So this will give you some value. So the ratio will be 100 is to whatever value you get from this particular formula. Okay. Now the second important concept is basically the McLafty rearrangement, that is the fragmentation. So among the fragmentations that have been asked in CSR examination, 90% of the times the fragmentation is basically revolves around the McLafty rearrangement. Okay, so what exactly is the McLafty rearrangement? Basically you have an oxygen over here, and this oxygen, basically you have to see if the molecule has a delta hydrogen. Okay, so this is the alpha carbon, this is the beta carbon, and this is the delta carbon, and you can see in the delta carbon we have a hydrogen attached. Okay, so what is the possibility over here? This oxygen will abstract this hydrogen like this. Okay, and once it abstracts the hydrogen, what will happen? This alpha beta bond, okay, this alpha beta carbon bond will break apart. Okay, so it will break apart, there will be a homolytic cleavage that will take place. So ultimately what you will get is, you will get an alkene over here, because obviously this will also fragment like this. So you'll have basically R dash free radical over here and a free radical over here. These free radicals will combine to give you an alkene, and along with that you will get this. Okay, this is the species that you will get. You can see there's a double bond that is generated over here, and this has abstracted the OH, and this is the molecular ion that is being generated. Okay, so this is the McLafty rearrangement. This is another example of the McLafty rearrangement, where what has happened is that you can see again alpha, beta, gamma. Okay, again the same principle can be applied over here, and in this case also the same fragment, it will abstract this particular fragment, and you can see that the McLafty rearrangement has taken place. So it can take place for ketones, it can take place for esters, it can take place for aldehydes, for carboxylic acids also. So be careful. Okay, this has been asked number of times. There are a lot of previous year questions that you can practice on this concept if you want. Okay, otherwise it's a simple and straightforward concept. And coming on to another important fragmentation is for your aromatic compounds, where the tropylium ion is formed. So if you have a molecule like this, and let's say there's some R dash also, okay, or whatever it might be. So over here what happens, the fragmentation takes place from this end. Okay, sorry, one of the hydrogens will get fragmented. Okay, one of the hydrogens, there are two hydrogens, so one of the hydrogens will get fragmented, and what you will generate is basically a tropylium ion. So this over here is called a tropylium ion. So what happens in this case, in these cases, is there is an expansion of the molecule. Okay, so this is a tropylium ion, and this fragmentation is very important. Okay, it happens for aromatic compounds. So these are the two important fragmentations. One is McLafty and one is this fragmentation of the aromatic compound. Now this has not been asked before, but if alcohols are given, generally it is being seen that alcohols do not have a molecular ion peak. Rather, they have a molecular ion minus 18 peak. Okay, so this is an important thing that you need to remember, because alcohols are generally very unstable in the form of molecular ions. So what happens is one water molecule is removed. So once the water molecule is removed, you get a M minus 18 peak, which is very stable. So generally for alcohols, this is observed, that you observe a M minus 18 peak. So again, it is important from an exam point of view. So these were some of the important concepts which came from mass spectrometry, or which are important from mass spectrometry. Now coming on to NMR spectroscopy. In NMR spectroscopy, first important concept is that talking about the shift values, the chemical shift values. So for aldehydes, it is for the CH bond, it is from 9 to 10. For OH bond in carboxylic acids, it is around 11 to 12. I'm again strictly restricting myself to the exam from an exam point of view. Okay, then this is a very important chemical shift value, that is the CH bond attached to a heteroatom, in particular oxygen. So an oxygen which is attached to a carbon, in that case the CH chemical shift value ranges from 3.5 to 5. It is very important from in basically questions which are basically asked from structure elucidation. That means 4 structures are given and some data is given, and in those kind of questions, this particular chemical shift value is very important. Generally what is seen is they will try to compare this CH stretching frequency, sorry, not stretching frequency, this CH chemical shift value, and this proton this hydrogen's chemical shift value and this hydrogen's chemical shift value. Okay, since I was in the zone of IR spectroscopy, I was comparing the OH. Okay, so this hydrogen over here, this hydrogen over here. So this hydrogen has a chemical shift of 9 to 10 for aldehydes. This hydrogen has a chemical shift of 11 to 12. This hydrogen over here has a chemical shift of 3.5 to 5. This is the range. And this hydrogen over here has a range of 2.0 to 3. So generally, sometimes I've seen a lot of questions where they compare this hydrogen's chemical shift and this hydrogen's chemical shift. So this is how you can make the clear difference. Okay. The second is about the J value. This is again important from a point of view of questions, that trans coupling is basically having a J value of 12 to 18 Hertz. Okay. And cis coupling has a value of 6 to 12 Hertz. Another important feature is that if you compare ortho coupling in aromatic compounds, then the J value is around 6 to 10 Hertz. But when you talk about meta coupling, that means meta coupling is this coupling between these two hydrogens, then the value comes down to 2 to 3 Hertz. Again, a very important question from exam point of view. Then when we talk about the hydrogens in a cyclohexane molecule, which is in chair conformation, so over here also J value varies. So if you're comparing two hydrogens in the axial position, the J value will be the highest. If we compare a hydrogen in the axial and one in the equatorial position, then the J value will be little low. Okay, compared to axial. And then if we have both of them in the equatorial position, then the J value will be the least. So again, this could be a very good question that can be asked in the examination. If you want to know how the J value is varying and why it is varying, you can read about the Karplus equation. Okay, Kapler's equation. This will tell you that how the dihedral angles, the change in the dihedral angle, that is a change in the angle of the planes between both the hydrogens, leads to a different value in the chemical in the coupling constant. Now, one exceptional case is the cyclopropane system. In the cyclopropane system, what happens that the cis coupling is actually stronger than trans coupling. So cis coupling is around 6 to 12 hertz, but the trans coupling is only from 4 to 8 hertz. Okay. And one more important factor that a lot of students confuse is that the J value, that is the coupling constant, does not change with the frequency or the magnetic field. Okay. A lot of other factors change, like for example, the nuclear population changes, the number of atoms in the ground state and the number of them in the excited state on change of magnetic field. Okay. Then the chemical shift value in hertz also changes, but the coupling constant does not change. Okay. Then coming on to DEPT, again a very very important concept. So when you talk about DEPT, so this has not been asked in the examination before, but like it has been asked before, but a long time back, and I have been expecting it for a long time now. For the past 1 year or 1.5 years, I have been saying that DEPT is important. I don't know when it will come. Okay, so hopefully अच्छे दिन तो आए नहीं, पर शायद DEPT आ जाए इस बार. ठीक है. So coming to DEPT 45, 90 and 135. In DEPT 45, what happens is that this is basically a part of 13 CNMR. Okay, so the protonated carbon signals are seen. That means that if you have a quaternary carbon, okay, if you have a quaternary carbon, then that will not be seen. Okay, so this will tell you that if there is a quaternary carbon present or not. Okay, and then we talk about DEPT 90, then only carbons bearing one proton will be seen. That means only the CH proton will be seen in DEPT 90. In DEPT 45, CH will be seen, CH2 will be seen, CH3 will be seen. Okay, but simple quaternary carbons which do not have a proton attached, they would not be seen in DEPT 45. In DEPT 90, only CH proton will be seen. Okay. And now DEPT 135 is actually very important, because over here what happens, again the quaternary carbon is not seen. So it is like DEPT 45. In DEPT 45 also quaternary carbon is not seen. So over here also in DEPT 135 also quaternary carbon is not seen, but here there are phases. So there might be a peak on top and there might be a peak in the bottom. So in the bottom it is called negative phase, and if it is on the top it is called positive phase. So so protons CH and CH3, basically odd protons. So odd protons are seen in the positive phase, and the even protons, that is CH2, will be seen in the negative phase. Okay, so again from DEPT you can find a lot about the molecule, and I feel it is very very important and it might be asked anytime soon. Next concept is chemical and magnetic equivalence. If everything that I have talked about till now was new to you, or you were not very confident, or you did not remember many of the aspects that I talked about just before this slide, then I would tell you to skip this slide, because this is a little advanced topic and it is a little confusing if you're doing it for the first time right now. So if that is the case, I would tell you to avoid this. Okay, you can read more about it, but I'll try to keep it to the minimal. Around 28 minutes have already gone, so I think this is the last or second last slide. So yeah, I think this is the last slide. So I'll keep my so let's start off anyway. So now coming on to chemical and magnetic equivalence. So chemical equivalence is basically something to do with the resonating frequency. That means if two atoms or if two hydrogens or protons, whatever might be the case, if they are having the same chemical shift, then we can say that they are chemically equivalent. Okay, we can say they are chemically equivalent, and they also have a similar environment around them. But when we talk about magnetic equivalence, it is not that simple. So what does magnetic equivalence tell you is that first of all, the chemical shift values have to be the same, but along with that, the couplings should also be the same. Okay, what I mean by that is, if you look at this molecule over here, let's say X is one substituent and Y is some other substituent. Okay, now if you look at this molecule, it does have a plane of symmetry which passes through this. Okay, so once it has a plane of symmetry, we can say that this HA proton and this HA dash proton, and similarly this HB proton and this HB dash proton, they both have the same, they both will be having the same chemical shift. That means the both in the blue ones and the both hydrogens, the orange ones, they will have the same chemical shift value, which is true, right? So they are chemically equivalent. They both are chemically equivalent, but when it comes to magnetic equivalence, they are not magnetically equivalent. That is why I've labeled them HA, HA dash, HB and HB dash. They are not magnetically equivalent. What I mean by that is, see, the chemical shift values for this and this is same. I agree. But when you talk about the coupling values, okay, so if you look at the coupling value, this HA will couple with this HB in an ortho position. Okay, it is an ortho to the HB. So it is having a ortho coupling. But when you talk about HA and HB dash, they will have a para coupling. So HA and HB dash will have a para coupling. Now I know there might be some confusion. You might be saying that HB and HB dash protons are the same. Okay, because of the symmetry element. Okay, and that is true. They are same, but chemically they are same. Okay, this is where the confusion will start. So that is why I'm telling you that if you are basically reading this topic for the first time, I would tell you to avoid it, because I have taken this because there might be a question in the examination where they might ask you if these protons are chemically or magnetically equivalent. They might select two protons and they might ask you whether they're chemically or magnetically equivalent. So that is why I thought it's an advanced topic. It might come in the examination. But before that, if you want to understand it, you will have to read in depth about it. Okay. So anyway, HA and HB over here have ortho coupling, and HA and HB dash have para coupling. But when I talk about HA dash, so HA dash has a ortho coupling with HB dash. Okay. But now it has a para coupling with HB. Okay. So they are chemically equivalent, but magnetically they are non-equivalent. Okay. Again, I'm saying it might be confusing to you. So if you want, you can go ahead and read from other sources also. But this is how it works. Okay. Chemical equivalence and magnetic equivalence is different. Now you might be asking, why are they different? Okay. What is the difference between both of them? And what is the importance of magnetic equivalence? So generally you would see that for chemically equivalent molecules, you will see a first order spectra. Okay, what I mean by first order spectra is that you draw a tree diagram. Like if there's one signal, that one signal will split into two signals, and those two signals will split into three signals. Like that, we talk about the tree diagram. Okay, so this is called the first order spectra. But for protons which are not magnetically equivalent, you don't observe a first order spectra. That is why if some of you have actually seen a NMR spectra, you will see that you never observe such peaks. Like you never observe simple doublets unless the molecule is very simple. If the molecule is complicated, you never observe doublets and singlets. They are always very, very, like this. These peaks are very, very complicated, and that is because those protons are chemically equivalent, but magnetically they might not be equivalent, because of which you never observe a first order spectra. A second order spectra is observed for such atoms or such protons. Okay. Okay, and then finally there are some miscellaneous topics that you should do, which are from your 12th standard. That is index of hydrogen deficiency, nitrogen rule. Nitrogen rule basically states that if there is a odd nitrogen, if there's a odd nitrogen present, that means 1, 3, 5, then you will observe a odd molecular weight. Otherwise you might observe a even molecular weight. Then please do topicity, because topicity is directly related to NMR, because if the protons are distereotopic, then they will give a different chemical shift value. Okay. And then one miscellaneous topic that you can cover if you want, I've just written it down because that is one of the important topics, that is solvent effects on the spectrum, on the UV spectrum. Okay. Because such questions I have seen before, that's why I thought I will include this. I'm not giving you the explanation, but you can do these miscellaneous topics apart from what I have taught. Okay. So anyway, I hope that the video was helpful. And I have tried to cover the most important topics from an exam perspective. And I thought I would be able to complete it in 10-15 minutes, but clearly it took a lot more time. So anyway, if you like this video, please give it a big thumbs up and do not forget to share it with your friends. It really motivates me, and I will keep on making more such videos which are quite helpful from an exam perspective and in general as well. Okay, so thank you, and I will see you in the next video. Signing off. Hey guys, so I'm a verified educator on Unacademy, and along with that I'm also available on the Unacademy Plus platform, where I'm taking live classes along with other educators. So in case you're interested in attending the live classes, you can subscribe to the Unacademy Plus platform using my referral code, that is SETHI, and that will give you 10% discount. All right, and in case you're not interested in attending the live classes, you can watch the free courses that are available on the Unacademy. For that, all you need to do is go to the Unacademy website or download the Unacademy Learning app and search my name over there, that is Ace Haiti. Once you do that, you will get the access to all the free courses that are available on the Unacademy platform. All right.